You've seen those incredible, detailed MRI images, right? But have you ever stopped to think, how on earth does that giant machine know if a signal is coming from the tip of your nose or the very back of your brain? It's this amazing spatial puzzle, and you know what? Today, we're going to solve it together.
This is the big question, isn't it? It seriously seems like magic, but it's not. It's actually this incredibly clever use of physics that works just like a GPS system for the protons inside your body. So let's dive in and see how it really works.
All right, to get to the bottom of this positioning puzzle, we have to start with the signal itself. Before we can figure out where a signal is coming from, we first have to understand what that signal even is. And it all kicks off with a tiny little wobble.
That's it. The signal we're looking for comes from protons doing this thing called processing, which is really just a fancy word for wobbling, kind of like a spinning top. The whole MRI scanner is basically just a super sophisticated antenna, listening for the specific radio frequency of that wobble. But, hearing all the protons wobbling at once is just noise. To make an actual image, we need a map.
Okay, section 2, the signal and the slice. So to create our map, we've got to set up a coordinate system. For an MRI, that means we have to separate the direction of the main magnetic field from the plane where we're actually going to measure the signal. Let's make that super clear.
So here's the deal. The main magnetic field, that's our z-axis, runs straight from your head to your toes. Now, as long as the protons are lined up with it, we can't hear them. They're basically invisible to the scanner. To get a signal, we have to knock them over into what's called the transverse, or XY plane. That's where they start to sing a tune that we can actually pick up. And honestly, this analogy just nails it. Think of the big magnet creating a personal north and south pole right through your body. The scanner doesn't really care what's happening at the poles. It's listening for all the action, all the signal that's being generated right there at the equator. That's our transverse plane.
So, section 3, phase encoding. We can think of this as our compass. Okay, so we've excited a whole slice of protons, and now they're all spinning and singing in that transverse plane. How do we tell one from the other? Well, we start with our first coordinate, phase encoding. But before we get into that, let's clear up something that trips a lot of people up.
This is such a good question because it gets right to the core of a tricky concept. A gradient gets applied, right? So it's totally natural to think it must be adding energy, that it's exciting the protons. But is it?
And the answer is a big, emphatic no. This is so important. The excitation part, that already happened. Phase encoding isn't about creating the signal. It's about stamping a unique spatial barcode on protons that are already singing their song.
This table breaks it down perfectly. The RF pulse is like the starting gun. It adds energy to create the signal. The phase encoding gradient comes after that. It adds zero energy. All it does is briefly change the speed of the protons to create these unique phase shifts, which is how we tag their position.
Okay, let's walk through it. First, boom, the RF pulse excites the entire slice. Then, for just a moment, a gradient pulse is applied from top to bottom. Protons up at the top speed up a little, and the ones at the bottom slow down. When that gradient shuts off, they all go back to the same speed, but now they're out of sync in a very specific, predictable way. And just like that, we've tagged which row they're in.
All right, section 4, frequency encoding. This is our map. Our compass, phase encoding, has given us the correct row. But a row has a lot of protons in it. It's not a specific location yet. We need a second coordinate to find the exact spot. And that brings us to our next tool, frequency encoding.
And just like last time, let's bust a common myth right away. Frequency encoding isn't tied to a specific axis, like the x-axis. It's a job that the scanner assigns. Its whole purpose is to make protons in different columns sing at slightly different pitches or frequencies when it's time for the final signal readout. And this table just shows you how amazingly flexible the whole system is. See? For standard cross-section and axial image, the machine selects the slice along Z, phase encodes along Y, and frequency encodes along X. But if you want a side view, a sagittal image, all those jobs get reassigned. The computer just needs 3 directions that are perpendicular to each other to make it all work. It's pretty cool. This is the million-dollar question, right? If they both help us find the location, why the complexity? Why do we need 2 different systems? Well, the answer comes down to efficiency and the physics of what the machine can actually measure all at once.
This stadium analogy makes everything click into place. Think of it this way. Phase encoding is the slow part. It's how we find the correct row in the stadium. But we have to repeat that whole process for every single row. Frequency encoding is the genius shortcut. Once we've found the right row, it helps us find the exact seat by making each one sing at a unique frequency, which means we can listen to and record all of them at the same time.
So, Section 5, from code to image. We've got our compass from phase encoding and our map from frequency encoding. We've collected all this raw data, but it's all in code. How in the world do we turn that into the anatomical picture we all recognize? We need a navigator to interpret it all. So this all happens during what's called the readout. For just a few milliseconds, while that frequency encoding gradient is turned on, the scanner's receiver coil just listens. It listens really intently, and it records this complex sound, this chord made up of all the different frequencies from that one row, all mixed together.
That is a perfect way to put it. The scanner records this jumble of phases and frequencies in a sort of data library called K-space, and it's not an image yet, not even close. It's a code that has to be translated, and that master translator is a mathematical process called the Fourier transform.
And I absolutely love this analogy. Think of the raw data that we collect in K-space as a really complex sheet of music. The Fourier transform, well, that's the orchestra that knows how to read the sheet and play all the notes perfectly. And the final MRI image, that's the beautiful, coherent song that you actually get to see.
And this just brings it all home. It's the perfect summary of everything we've talked about. Phase encoding is the compass that gives you your latitude. Frequency encoding is the map that gives you your longitude. You absolutely need both to pinpoint the exact location of every single signal, and when you put them together, they build this incredible, detailed map of the human body.